Okay. Thank you everyone for coming. This is actually our last seminar this year in the salle de séminaire. The next one will be after the inauguration of the new amphitheater starting from next week. And so today, as our first seminar of the year, but last seminar of the salle de séminaire, we have Oliver Hahn coming. So Oliver did his PhD at the ETH in Zurich from 2009, and then went on to Stanford, CAPAC, for a couple of years, then went back to Switzerland with an Ambizione fellowship as an Ambizione fellow. And then for 5 years, he was a professor d'université at Université de la Côte d'Azur before moving to Vienna, where you are currently. And so Oliver has been working on quite a lot of different things, and today he's going to talk about mostly cosmological simulations and N-body simulation, which he's an expert of, and well, we'll probably talk better about it. So
I don't know.
Yes. So well, the floor is yours, and
thank you so much. Well, thanks so much for having me, especially also Stefan, who invited me for the whole week. Exactly. So I think I realize I'm now at the age where I give this review, and I have things like history in the title. Let's see how that goes. Most of the history I didn't firsthand live through, so just want to do a little bit of advertising. If you're interested in more details, so quite a bit of this is in this review article that we wrote a few years ago, now already 2022, with Roland Gulo. But now let me start. Do we have a pointer or something actually? I could use a stick. A stick is good. It used to be. It's the usual. A stick and a carrot will do.
Just a stick. Or maybe you can start on look for a stick.
Okay, yeah. Well, so basically today, we'll talk about cosmological simulations, or cosmological simulations means simulating the universe. And what goes into simulating the universe, I think now we have a very complete picture. This has not always been the case. Of that we have a sort of best guess is we have an early inflationary phase where we don't really know what's going on. We don't really understand the inflaton yet. We don't understand potential. We don't understand if maybe there are other models that sort of work better. Then we have the early sort of plasma phase of the universe, which we can model very accurately. This is, of course, the map from the Planck satellite, where you see the cosmic microwave background. That's sort of the first electromagnetic measurement that we have of structure in the universe. If we wanted to look before that epoch, we would have to use gravitational waves or neutrinos. And the picture then is that from these sort of seeds of structure under gravitational collapse, we form this very inhomogeneous structure here of the distribution of galaxies. So each point here is a nearby galaxy. This is from the 2-mass survey. And of course, you see here the Milky Way in the middle. And so each dot of them is, of course, made up of a large amount of stars. We have all of galaxies. So if we want to model this, basically we go through this whole history. And I think we have a very, very good sort of framework now, multiple, to simulate all the way from here to here.
Can you try resharing the Zoom, because apparently it doesn't. Sorry, it doesn't show up anymore on the Zoom.
C'est bon. It's good now.
It's not good.
We've lost it here.
We have to lose the amphitheater clearly.
Are you
Well, you have to imagine now that this
slides?
people on Zoom.
From the people online, no, we can't see anymore.
Sylvia, it's Sylvia, Florence Duret, just to know.
Et du coup, si on se remet en mode vidéo, alors j'étais en...
That's also nice.
Oh,
There we go.
Okay.
There we go.
Okay. Sorry.
Okay. So where was I? So we can simulate basically from all the way from here to here, and I'm not going to talk about all these pretty galaxies that we can produce in simulations now, but I want to sort of talk more about the large-scale structure aspect, and that is basically this is only a small number of modes that we can access and sort of infer cosmological information. Much more of the volume and an imprint also of what happened much later in the universe is in the large-scale structure data. And so how do we model this? So in the end, what goes into this modeling? Well, what is happening now? Annotate. Yeah, not sure. What basically goes into the model in the end, we have sort of a lambda CDM model, which is a collection of parameters, so on the order of 6 or so. Then you can extend it now with massive neutrinos, the dark energy equation of state. You can add anything you wanted to add on top of it, and the usual assumption that we have an underlying Friedman universe. You can write down the equations for this and to solve this perturbatively. And for this, you need actual nonlinear simulations. So I will mostly talk about this aspect. And so we have this complete picture now. Now we know, I guess, as a student now, when you grow up with Planck, you grow up with galaxy catalogs that have millions or maybe soon billions of galaxies in them. This was not always the case. And so I wanted to add a little bit of a historic aspect to it, sort of how some of this picture emerged, because I found it quite fascinating when we were doing the research for the review article. So I don't have first-hand recollection. I wasn't really there in the 70s for most of this. So I apologize if maybe something is missed. But so the first, not the first N-body simulation, but the first cosmological simulation I could dig out of is actually by Peebles, 1971. He's not exactly known as a simulator, but actually he ran the first. And it was a spherical simulation. And one of the big questions was back then, basically, if the rotation of galaxies can be explained by gravitational collapse. So put basically down some random points in an expanding universe and wanted to check whether sort of once they collapse, you see here some structure forms, whether the angular momentum that this would acquire is consistent with the rotations of galaxies that you had. And so in principle, this worked. Magnitude-wise, it didn't, and so on. The technique was one where these points were just mutual interactions. So they were really points, point masses that were interacting pairwise. So for n masses, you have to calculate n-1 interactions. So the whole thing is order of n square in the gravitational complexity. And so in 1971, the best you could do, or the best data was 90. There were, of course, N-body simulations earlier, but they were mostly like, for example, Michel Hénon is one of the pioneers also in France for N-body simulations already in the 60s. I think the very first ones even in the 50s, but those were more star clusters related simulations. And then it really sort of took off. The first, to my knowledge, periodic box simulation done in 1975 by Miyoshi and Kihara. If you look at this, only 54 citations, so it might have been important in the 70s, but then people forgot about it. And so what you see here now is a two-dimensional simulation and of 400 particles already with periodic boundaries. I will say in a moment about this. And so the points are distributed initially randomly, and then sort of some structure emerges. And I think you sort of already see that this looks much different from this one here. And it kind of, thank you very much. And you kind of get the idea here at the end that maybe some of this kind of web-like pattern emerges that we've seen in the galaxies. So let me maybe even go back. So these filamentary web-like structures that you see here in the data. Of course, also data of this quality wasn't around back then because galaxy catalogs had maybe 1,000 galaxies or something like this. Exactly. So one question back then that wasn't obvious is, what happens to systems when they collapse? Do they decouple as expected from the expansion of the universe? And we all know that sort of the Laser-Irvine equation tells you that. So something that is virialized decouples from the expansion of the universe. And so that would actually be the main result of this paper. Let me go back to why periodic box. Why is that important? Well, we know so far the universe should have no boundary, right? So if the Friedman hypothesis holds, then it's either a maximally symmetric space of positive, negative, or zero curvature. Other topologies are possible. And so the simplest thing they can do is make it a torus, which makes it basically unbounded but finite, right? So you have no boundary because you glue together two sides and the other two sides and the third two sides. So it's like a piece of paper that you roll up, but then it's not 2D piece of paper, but 3D. And so you get a three torus. And the nice thing is, because of this, also immediately mathematically, the Laplacian Fourier series is an eigenbasis, and so you can always use FFT to work on these spaces. The nice thing is no boundaries, and this translation invariant. Translation invariance, of course, is the homogeneous property of maximally symmetric spaces. But it's not rotational invariant, right? Because, for example, the particle itself sees itself not isotropically at the same distance in all directions. Because of the periodicity being in the practicum. My move goal for the day was achieved. Maybe I should say more still. So very recently, people actually challenged this. So it's a very, very nice paper by Gabor-Raj with ideas from mathematics. This is the only sort of what I'm aware of that tried this. So the idea is to give up on the translation invariance, but build in the rotational invariance. And you can do this by compactifying the Euclidean 3 space onto a sphere. So the idea is basically your real numbers, and you project them to the intersection points on the circle. And so this point here ends up here, this point ends up here, and the point at infinity ends up on top of here. So you can map all your points on the circle or in 3D. Then you map them onto free sphere, and you embed it in R4. And you can run simulations with this, and it's kind of funky, because now if you discretize the mass, in some way now the masses sort of your particles start to increase to the outside, and you get sort of a weird zoom picture of a small region where you have high resolution and then it drops. But let's go back in time. The next sort of, I think, interesting development was then happening more towards the end of the 70s. This is from a Scientific American article. This is reaching already 2,000 particles with direct summation. So now you can do this real time on your GPU and the laptop without any problems, but again, it's challenging. Again, a spherical simulation. And what I found interesting here is that actually, for the first time, they talk about a gas of galaxies, and sort of this picture emerged that we go to a continuum limit of galaxies. And so there was a lot of discussion. Actually, it's very interesting. We go through it, talk about BBGKY hierarchy and sort of connecting, talking about galaxies to talking about ionized gases. And so BBGKY hierarchy then was used by Davison-Peebles in the late 70s sort of to cook up theory for the large-scale structure. So let me make basically this connection more from the theory side. So this BBGKY hierarchy to Vlasov-Poisson limit sort of emerged in the 60s already. These are the references I could dig out for this. What is BBGKY? It's basically, if you have n-bodies, you can describe the system as a hierarchy of n-point distribution functions, and then basically a one-point distribution couples to a two-point to the three-point, so you get full hierarchy. And so basically, this gives you this hierarchy, and if you neglect two-point body interactions, meaning you go to the continuum limit, this truncates the hierarchy immediately, but you neglect two-body effects, and in that case, you get the Vlasov-Poisson system, which is just the evolution equation for the one-point density. Right? Okay, looks like this. So this makes kind of a connection between talking about galaxies as points in space and talking about a continuum. Right? Which I found interesting, sort of happened around the late 70s. So what does this equation tell us? This is a transport equation, and this is Poisson equation. So Poisson equation couples then the mass back and tells matter basically how to accelerate due to the presence of overdensities. Never mind the details. Let's quickly understand how we solve this. To make it simpler, let's remove the expansion of the universe, and let's remove the acceleration term. Then we just have an advection equation, linear advection. So I hope you remember this from your math courses. And linear advection equation has the solution. So this is space, and this is time. And all it does is it transports the initial conditions along straight lines forward in time. So if you want to know the solution, basically you just have to go back along x minus vt to where it started, and it's given by your initial data, right? So basically preserves the density f along these characteristic curves. And that's behind an n-body simulation in the end. So you go discrete from the galaxies to the continuum, and then you go back to discretize it again. So we'd call this now the Lagrangian map. It's no longer straight lines, but we have some patch of stuff that goes into some other patch of stuff, right? And we describe this mapping in full generality. Let's not bother what it is. And now we discretize it again with particles and consider this mapping. And now we're talking sort of, we're going one forward and then one backward again. So we have a discretization as an approximation to the continuum system. Why is this important? Well, now we can talk about, right, resolving multiple galaxies with one fluid element or things like this, right? Okay, there's another interesting thing. So when you then write down the equations, actually, and you change your time coordinate to the scale factor of the universe, so never mind the technical details, it's basically just plug in your equations. You see that if you take a to 0, this acceleration term drops out, and you get this equation here, which you can write asymptotically and then the limit a to 0 simply as this. And this you can solve, right? This is a gradient of some scalar function of the initial conditions, and here you just have a time derivative. So the solutions are straight lines, and you have what's called the Zeldovich approximation, which was derived not on these grounds, but sort of a bit more heuristically by Zeldovich in the 1970s. And it turns out this is actually a solution that's exact for in one spatial dimension. So this is the 1970 approximation. Mass moves on straight lines with a perturbed initial scalar field. And there's a beautiful movie from the 1970s, from Soviet Russia. I'm not making any propaganda here. So it's very interesting. So this apparently was shown for the first time by Zeldovich himself in 1977 on a conference in Tartu in Estonia, where they were sort of Western cosmologists and Eastern cosmologists met. So they had 2,000 particles, and they didn't solve the full n-body system, but they, unfortunately, I should have speeded up. So basically, they generate some initial conditions and then evolve the particles forward under this approximation. And what you see nicely is how these sort of filamentary structures now actually emerge. Let me speed it up a little bit. So you see how this sort of starts folding onto itself, and how you start forming a filamentary structure here. And then they also did others, like with more power in the ultraviolet, so more small scale fluctuations, network structures here. Even bluer, and then it starts being more and more clumpy. Good. So this were now sort of, for the first time, sort of, I think this continuum picture now started to lead to understanding of how this 3D structure of the cosmic web started to emerge. Today, the picture of this simple matter moves along a straight line has actually been extended into a fully rigorous perturbation theory, which is called Lagrangian perturbation theory. And so the idea is basically you take these straight lines and then you decorate it with interactions. So you have a first order correction and so on and so on. So things moved in a parabola and so on and so on. So you write it down as some sort of power series with coefficients, how the matter moves from here to here. And since not so long ago, actually, well, the recursion relations for the perturbation theory of large-scale structure were known already since the early 80s, but not for in this picture. In this picture, sort of first steps to higher order were made in the early 90s, and then the recursion relations were derived mostly in 2012, 14, 15 by Cornelius Rumpf, Uriel Frisch, and Jelidovsky, and Matsubara. And so this is works actually extremely well. So you can predict the distribution of matter on large scales extremely well, up to the point when sort of these filaments start to emerge or things start to cross over each other, which is a problem for the theory, because then sort of this Jacobian that you have here becomes multi-valued, and you have to then sum over non-local contributions, and it's an unsolved problem still to this day to do this there is some attempts by Stefan has worked in this direction. It's called post-collapse perturbation theory. But in a general setting of having a random field like the universe, of doing this everywhere, it's an unsolved way. So people resort to effective field theories to sort of integrate out these degrees of freedom and then fit effective parameters to get in this regime. I think I'm needing much more time, so let me step over this. There's something other that's sort of very interesting is if we go back to our Vlasov equation, then the characteristic curves that come from that actually become these two curves. So it's a time derivative of x. It's just a scale factor contribution to the velocity, and the acceleration is given by the gradient of a potential. And so I mentioned we have a continuum limit. Now we discretize it. So in some sense, these characteristics would be exact if we would know phi, but we have to approximate phi because we only have a discrete number of tracers, if you want, of the mass, right? So that's where an error now is made, where we replace basically, if instead of the continuum limit, we approximate f with something like an empirical distribution function that we estimate from the particles themselves. And the simplest is to just treat them again like individual point particles, or you can make them a little bit extended, which is nicer because then they don't scatter off like black holes or something like this with each other. Exactly. The cool thing is these equations actually, and that's deeply connected to the structure of Vlasov, actually have a Hamiltonian structure. And so Hamiltonian systems, as you know, there is a lot of mathematical theory about it. And especially we have excellent integrators for solving these numerically. So we can exploit this Hamiltonian structure when integrating these equations. So let's look at how now the full nonlinear evolution would look like. So this is, sorry, let me go back. This is a 1 plus 1D perturbation. So in velocity, it's just a sine wave. Here is position, here is velocity. So stuff here has a positive velocity, starts moving to the left. Stuff here has a negative velocity, starts moving to the right. And then because the density here, more fluid elements are in the center, it starts pulling into the center, then it crosses through and it falls back in. And so if we plot this in a space-time diagram, it actually looks like that. So this is now the coordinate here, position, and this is the time. So now our Zeldovich approximation, we see it right here. That's the straight lines of the fluid elements, and that holds exactly until the moment when multiples start to cross over each other. And that's where sharp things emerge, like caustics. And that's why it's mathematically very, very hard to make progress here. So in plasma physics, this would be called monokinetic or single-valued mathematically. And this regime is multi-kinetic, but it's not thermalized, right? So you see you have discrete number of streams, particles that have correlated velocities, but they're not thermalized to any known distribution, at least not at early times. This is a very hard regime to solve. Okay, let's briefly going back. If we now think about the history, sort of, I think most of this picture was there now. Okay, we can sort of solve these systems, and we have to just throw more and more particles at it. But throwing more and more particles to approximate this collisionless regime means you have to get around this n square or simple other methods. So a lot of development in the 80s to 90s was in terms of algorithmic developments. Particle mesh, for example, was already developed in 73, but it took almost 10 years until it was applied to cosmology. This is an adaptive version by Couchman from the early 90s. Exactly, so the field really exploded in the 80s. So these are, to my knowledge, the first bigger particle mesh-based N-body simulations. Is there actually a time? I have no idea. I'm doing the time. Last, currently. Okay. Good. I think for then the ballpark of the developments, this was very crucial. The inventing hierarchical methods. Actually, I think the first one, or the most famous one, was Barnes and Hutt. It's named after them. There's a paper by Appel from a year before. So the idea is there, you give up on solving an exact sum like in the n square or using Fourier methods, which are not adaptive, where you're restricted to sort of having a cover your whole domain with equal sampling points. But you approximate it by some space partitioning, and then you approximate the force. How does that work? So if I want to calculate the interaction between this point and this group of points, maybe I don't need to know, I need to calculate interaction with all of these three, but I can sort of approximate these with a common mass, for example, put in the center of mass, and that is fine. So if something is further away, I don't need to go so deep. That's basically the idea. And exactly, so if you have a cosmological thing, then sort of this becomes automatically adaptive. You split always, if you have multiple particles, you start splitting a cell until you have only a fixed number of particles in one cell. And then you have multiple options. Either you try to find a method to solve directly on the grid structure like this. This is then what AMR solvers are doing, multigrid like in Ramses, or adaptive multigrid like in Ramses or in ENSO, for example. Or you do a hierarchical multiple expansion like in the Barnes and Hahn. So how does that work? In each of these cells now that you have here, right, you perform a multiple expansion. And when you do this, you can bound the error that you're making. So you get a monopole contribution, a dipole contribution, quadrupole, and so on. And these are proportional to 1 over distance, to the distance from the expansion point over the distance from where you want to measure it. And because this ratio, this distance here to this distance can be bounded, you can always control the error. So you can put an error bound on it and say, I can calculate it to a given accuracy. And so every time you add a term here, you have to add an additional power here. And there's an even more clever method, which was actually already developed in 1987 by Wingard and Rochlin, which is the fast multiple method. There, the idea is you not only do a multiple expansion on this side, but you also do a multiple expansion on this side. So you not only sort of compute the interaction between each point and the multiple expansion, but you compute interactions between multiple expansions and multiple expansions. And then you can show that that actually goes like order of the number of particles algorithmically, which is the best you can do once the tree is built. So this allowed actually sort of then to increase the resolution tremendously in these simulations, and was crucial to these measurements of what are the density profiles of these clumped structures, which was in the 90s, and then gave rise to, for example, the NFW profile, which is this famous double power law. Then there's some debate whether it's better fit by slightly different parametric form. But what is clear is that sort of halos are all these clumped structures have a very, very simple 1 parameter family of shapes, roughly, of profile shapes. And that picture sort of solidified. So there was some debate whether how much of this is caused by resolution until the early 2000s or so. That was thought so. But then already in 2010, all of a sudden people found, actually it's not true, not all halos are NFWs, but the first generation, when you have smooth initial conditions, actually turn out to be pure power laws in the center close to r to the 1 minus 1.5. I think to this day, we don't have a full picture of how all of this goes together. There are some theories for this that cannot account for this. There are some theories for this that do not fully fit together with this. So I think there is still some room on the analytic side.
Can you explain again what's the difference? You said something about smooth initial condition.
So if you put a cutoff in your perturbation spectrum, you get these. Like if you do CDM at the free streaming scale or warm dark matter simulations, yes. And it's always the first generation of structures to form actually is cut here. This slide I took from Florent Leclerc, who's where is he sitting there? So he should have given this talk actually, which puts all of this on one slide. So here it starts actually with non-cosmological simulations. This one here, this might be the people's one, I didn't check now. But what this interesting is showing is the number of particles versus time in a logarithmic here. So meaning this is exponential if it's a straight line. And I think you emphasized this in this blog post as well, that there is sort of a break in the 1990s where all of a sudden you actually see a scaling that's faster than exponential, which comes, of course, well, it's still exponential, but it's a different slope, which comes due to algorithmic developments like the ones we discussed. And so now we are on the order here of 10 to the 13, 10 to the 12, a few times 10 to the 12 to 10 to the 13 particles in the largest simulations to date. I think the very largest one has not been surpassed to this day anymore. Exactly. So that's a huge number of particles already. Just to look a little bit closer at from the last years, you see all of these sort of methods that are used is on the next one, are relying on tree or fast multiple methods in combination sometimes with these particle methods rely on Fourier methods. One beautiful example, of course, is also from the Euclid flagship simulation, this full sky light cone, tremendous structure. But maybe the more important achievement than just being able to run on bigger and bigger machines. So you see these all run on, this is in 1,000 cores. You're running on 500,000 cores of supercomputers. But maybe the most interesting achievement is that actually in the 2010s, there has also been a convergence in terms of the accuracy of all the methods. So before, people had crude tests and there was agreement. And then there was really a consolidation phase where I think by 2015 or so, all the codes were made to agree to percent or sub% level accuracy. And so that's a completely game changer, because before sort of we were in exploratory territory, right? You want to understand how structure forms. Now you become really predictive at the level of sub% level accuracy. And this is the reason why I don't talk about hydro simulations. This is now the same comparison from different models of galaxy formation simulations. And so you see it's not quite the same level of agreement. And in fact, it's not to be expected, because here essentially there are no free parameters whatsoever. Everything is only related to accuracy. So you can always tune your accuracy to be within where it should be. Here you have a ton of free parameters. And this is really a problem now, because you see this is fairly, so this is large scales, this is small scales.
The power spectrum of dark matter you're showing?
This is the the matter power spectrum, yeah. So, I mean, some of them may be unrealistic, but in any case, there's a lot of sort of theoretical uncertainty that we do not fully understand. So the only way to deal with this at the moment is by incorporating it and marginalizing them. Okay, let me go back. So to the biggest simulations. So they're all sort of employing the most best suited for parallel environments algorithms. Now, for example, this most recent one from 2024, New Worlds, also runs 24,000 GPUs. These are made to make basically the mock observations for LSST. And the Euclid one is not so far on from that. So the idea is that we basically use scale to the entire.
Can I ask a provocative question?
Yes.
So what's the point in making these enormous dark matter simulations when there's so much uncertainty in converting into observables with astrophysics? What's the interest?
Well, you want to build emulators that are accurate enough in the end for this part that you understand well, and then you add on top of that new models. I think that's the best you can do.
Okay.
Okay, let me skip over this. So one thing that we actually then started looking into. So now we have this, we can push it, we can always overcompute, but we all know resources are limited, and we should maybe not use more resources than we should have. So how can we invested a lot of time in my group into trying to understand how we can, at fixed resources, we can increase the accuracy more. And so one thing that was a bit disturbing to look at, actually, now we have an N-body simulation, and we have the continuum limit perturbation theory, and they should agree, right, in the regime when the perturbation theory is right, but they don't. So you undershoot. This is a ratio power spectra, again, small scales, large scales, and you undershoot tremendously. You can say, well, I have to have, I don't know, 100 particles before I can trust my simulation. But actually, it turns out you can understand where this comes from. This comes from that the particles are discrete objects, and you actually have two-body effects. They're not continuum. You're not in the continuum. And so your interaction is anisotropic at the scale of the particles. maybe your growth of perturbations is not the same. But once you sort of average over 8 particles or so, you start being fine. But then you have to give up. You have to use 8 particles at least per mode, right? That you can trust. So can you push it even further? And so we went. I'm not going to go. I don't have time to go into this. But basically, you can find trade-offs where you can push this much more, and actually you can go to below 8 particles to get converged answers. But you have to think with the order of your perturbation theory and to know exactly how to start the simulation. These are, for example, considerations that I have not got. How are you doing in the time? 40?
Probably 10 more minutes.
10 more minutes?
Ish.
Yeah.
What's your time with a technical mishap?
Interruptions from the audience.
10:15.
There's another interesting thing we looked at, and that puzzled me for about 10 years, I think, before we found the solution. Well, we know the universe does not just consist out of one single fluid that's collisionless and that describes all of the matter, right, in a cool way. But we can make it slightly more sophisticated and say, well, let's have 2 fluids that are both collisionless. One represents the baryons. We neglect any pressure or other effects. We just assume it's also collisionless. And the cold dark matter fluid. And we can calculate exactly how that should behave. And in fact, this is effects we know that baryons do not trace exactly the cold dark matter because they are coupled to photons until recombination. And so structural formation in baryons is delayed. And that's sort of a few percent effect at redshift 10, 8% or so. And it's an order 0.5% effect at redshift 0. So if you want to do next generation modeling, you probably should be able to understand this better. Exactly, never mind the details. So the dominant effect of this is what's called a isocurvature perturbation. And what that means is that if you fix your matter perturbation, then you basically have changes in the relative concentration of baryons and cold dark matter as a function of the location. So as baryon fraction basically changes as a function of location, even though the total mass does not change. Right? So basically you're just fluctuating the relative abundance of dark matter. And that is fixed. So that has a spectrum. It does not evolve first order. And then you can check whether that's actually true in a simulation. So you put in your simulation, and this is what people did, and it's all over the place. So you cannot reproduce even the linear evolution in the linear regime within this. And so it's again one of these effects where because you're modeling it with particles, you have sort of a relative contribution. And so luckily we actually managed to solve this. So once you understand it comes from an isocurvature perturbation, basically you have to perturb the masses of your particles, and then you can perfectly get this correct. And it's nice. So we basically can model these effects now as well, very small effects that change the relative abundance of the baryon fraction as a function of the spatial coordinates. Then basically the interesting thing is that once some structure collapses, this spatially varying baryon fraction starts being locked in. And so if you study high redshift universe, this might, if you want to do cosmology maybe with a high redshift universe, this might be relevant. It might also be relevant at late times. I think we don't know this yet, because this effect of the relative change in baryon fraction comes from the baryon acoustic oscillation. For those who don't know what it is, I don't have time, you can ask me later. And so basically this baryon fraction is correlated on BAO scales. And so if this correlates with galaxy formation, saying that, I don't know, on a BAO scale, you have a 1% higher probability on your selection function to have something in or out, then this might cause bias. So we have to maybe step up this further. Good. Now we heard about these modeling the continuum limit as particles. I want to just mention now in the last minutes that there have also been sort of a lot of efforts going beyond single particles. One, I call it metric methods. Vogelsberger might call it the GDE, geodesic deviation equation. So the idea is basically that instead of evolving particles, you try to capture the deformation of a blob in phase space. So if you start with a circle and you have an non-harmonic potential, then this gets sheared and deformed, but you can, because it's a Hamiltonian system, the area enclosed in this contour is actually preserved. So there's also water bag methods and so on that exactly try to capture this evolution. And so it's interesting that you can, of course, fold, like if you were to do lensing, now you just evolve the elliptic deformation of this blob. So you don't try to capture the higher order ones, but you just capture the elliptic deformation. And you can write down the equations of motion for this, and you can integrate them, in fact, along with your equations of motion. And that allows you now to basically say how much has my matter distribution been stretched out around a single particle, or how many caustic crossings, like these things that we've seen, remember, these sharp boundaries, how many has happened. So for example, a nice plot from the Vogelsberger paper, you look for chaos. If you have regions where basically this gets stretched exponentially fast, this is then indicative of the economic exponent that indicates chaos. You can also, and again, Stefan has worked on this as well, you can also, instead of treating particles, you can interpolate between them, and you can sort of restore a continuum limit. Either you put little triangles, or you can do it higher order. So the idea is, when you can do this Fourier, this is the thing that we do in our latest, is basically instead of having just your n-body particles, which are the red ones, you think of some interpolation of the positions between them, and you can then insert as many particles as you want. And especially at the early times, when these discreteness effects are large and affecting your linear evolution, what I showed before, this helps a lot, actually, to do this. You can add for free as many particles as you want and beat down. It's not actually very, very costly. Yeah, this is some stuff we did more than 10 years ago. Well, if you have just your particles, or if you oversample it with interpolation, you see all of a sudden there's all this connectivity now because there's sort of coherent deformation in the particle. To show this again, I don't have time for this. So one cool thing now is with this, and we need one more trick. We can actually sort of get very accurate simulations from the Big Bang started. So we don't even need perturbation theory. I'll show this in a second as well. We don't need this LPT. You can just integrate forward in time. And so this is because I've never seen it. This is a forward light cone from an n-body simulation. You always see like from an observer, but this is seen from the Big Bang. So basically photons that emerge from one point at the Big Bang. What is the evolution of structure that they see? And so you now get a feeling for sort of the surface or the number of modes you can probe from the CMB versus how much volume you in principle can access from a large-scale structure survey.
How big was the box to do that?
Here we were cheating. So there is some periodicity in here. Yeah. It was more to be able to do this, you needed to invent a few things because Hamiltonian integrators don't work, they blow up here. So you have to have a different integrator scheme. This was the last thing I wanted to bring in. I think a quite exciting thing is that sort of now we understand for the first time, I think, strange, or maybe people understood this before and I was not aware of it, how to actually bring together the perturbation theory side and the n-body simulation side, because so far it was always like, okay, you're either a perturbation theory guy or you're an n-body guy. But turns out you can piece them together and you can make sure that your integration is always consistent in an asymptotic, mathematically asymptotic sense to the Lagrangian perturbation theory calculation. And what's the main advantage of this? I'll show you here. You are, with a few steps, as good as the perturbation theory. So this is the second order Lagrangian perturbation theory prediction for the large-scale structure. It doesn't look very good. Why? Because we're pushed it beyond the point when these trajectories cross. So it's wrong, effectively. If you do one step with this new integrator, it looks exactly the same. Now, if you go to higher order perturbation theory, because you're outside the convergence already, you gain nothing. In fact, it becomes worse. You're already outside of the greatest convergence. But here now, if you do 5 steps, all of a sudden you have you start getting all the interactions that are necessary to get your collapsed structures. And then with 10 steps, it looks like this. If you used one of these standard symplectic integrators that are built into n-body simulations, and you only do 10 steps, it looks like this. So you think, this looks actually great. I have all this filamentary structure. But if you look at the large scales are not correct at all. So here you have a very strong filament sort of concentration here that's completely missing here. So you have to go to many, many more steps until this is there. The reason is that these integrators, they basically, instead of reproducing the Zeldovich straight line, they constantly overshoot, undershoot, overshoot, undershoot. And so you have to converge second order to a straight line, which is not optimal. You can mathematically formulate this, build this in. And so then the cool thing is, just for those, is again a power spectrum. So where standard integrator basically converges like this to the truth. So it's off on all scales, and you have to do n steps in order to be so and so accurate. These new integrators, they converge in a scale-dependent way. So they're asymptotically always correct. And so more steps you do, the smaller scales you get correct, which is a very nice property. And so with very few steps now, you can sort of get fairly large scales very accurate, which is perfectly the regime we want if we don't care about resolving the inner parts of halos, but we want to get the large scale structure. We want to get the volume that Euclid observed, something like this. Correct. If we do this, we give up the small scales, but maybe that's not so bad because all halos are the same, right? And they're all in FWs. They all have no hairs, well, to some extent. And so there's a sort of interesting development where people have been playing now with adding small scale resolution back in using machine learning. Basically, your large scales should inform roughly what's possible on smaller scales, and there should be not too much additional information. Then there's just halos of given mass and so on. And so people play it, and we also did this with diffusion models. That's the same stuff that DALI and so on are using. Exactly. So you start with a low resolution, and then you paint it in super resolution models, and you see you get all this additional structure. Now the problem with these is they're never super accurate. So you can get like 1% accuracy, but to push that further, it's not so obvious with machine learning how to do that. Okay. I will try to quickly show this because I think it's a little bit of a celebration of, I think, amazing work that's been done here by people that have been pushing this for a very long time. So now I think with this fast simulation, so that we get a very interesting regime. If we go to the CMV, right, so you might know you only have to measure the CMV spectrum and then you have all of it. There's no more information because this is Gaussian, so knowing the covariance tells you everything. And you can compute this then with a model and fit it together. For a non-Gaussian field like the large-scale structure distribution, highly non-Gaussian cosmic web, this is not true. So you can either go be a perturbation theory person and say, well, I do it perturbatively. So I go from 2-point to 3-point to 4-point and build my summary statistic like this. Or you cook up one of your favorite alternative statistics. And so, for example, this is like without any preference of one over the other. For example, for the wavelet scattering transform, it shows you that this is a power spectrum constraint and a cosmological parameters. It doesn't really matter what all you should see is that sort of you shrink tremendously by adding in non-Gaussian information. And in some sense, they all should. I think we don't understand fully yet which ones are more optimal, less optimal, what's the best maximum sort of improvement that you can get. But where there's something much more interesting that I think people here pioneered quite a bit is what's called field level inference. So the idea is, well, let's give up on this idea of compressing it into a statistics and then fitting a statistic into compressed data from the survey. Let's just fit the simulation to the survey because we can do it. And so people here have done this and have pioneered this method of cohort collaboration. Many people are here in the audience. So the idea is that you basically sample from the simulation as a forward model and then use a Bayesian model in order to invert this. And because it's Bayesian, can deal with incomplete data and so exactly. You probably have seen many talks here. And so basically right now to solve with simulations the complete inverse problem that we started off with, right? So sort of we have this forward evolution, we can observe only this, and now we want to go back to getting our model parameters back out because that's what we're interested in. And there's two ways that you can do this. Either you train a neural network with many simulation examples, so you need a fast simulation framework also for that, because you have to typically get in the order of 100,000, 10,000, 100,000 simulations in order to do this accurately. Then basically you sample from the likelihood of this or here, and you train, and then you sort of use a neural network to invert your data, or you do an explicit gradient based. So in either case, you need a very fast forward model, and it should also be differentiable if you want to do the second. If you want to do the first one, it doesn't have to be differential, but basically this approach here, because you're operating in super high dimensional spaces, so Guilhem or Florent can tell you all about this. You have to basically use good sampling methods like Hamiltonian Monte Carlo And so just a little bit of advertising ourselves. So we've been working the last years on a predictable N-body simulation framework that can do this, but there is many more on the market. There's JaxPM, QWD by other people, and of course there's also the Borg framework, which has been doing this for many years. And Florent has been also developing other methods that sort of improve on similar things like these fast integrators using Polar. Exactly, and so galaxies. So now we can model all of this. How do we make the connection to the galaxies? Well, we already said hydrodynamic simulations make kind of this impossible again. We cannot run hydrodynamical simulations right now. It would be great if we could do this, run hydrodynamic simulations with all the subgrid models and then fit it. But hydrodynamic simulations, as you know, they need millions of CPRs. So no way. We can maybe do this in 100 years, I don't know, unless we have improvements. Semi-analytic models, that's the old way of doing it, or HOD models and so on. They're, in principle, could be used, but then you need relatively high resolution in your simulation because you need to know halos, you need to know the merger history, then you put recipes on top of that. And so this will be very difficult. So I think in people now in this field where these are sort of the preferred methods for generating mock catalogs for surveys, you've got a high resolution simulation like the very big ones that we model, or semi-analytic models. But if you want to do this fast inference, then you need something that's much more approximate. So I'm not going to go into details here, but there is like these effective bias models or things like this that people are experimenting with in the field level inference. Yeah, so I just wanted to show some first work in progress that we can discuss this later, is where in the end, what you want to get is we want to see that with this field level, you can actually do better than standard summary statistics. And so it's very sort of all work in progress. I think just tricky in the end, we get both unbiased results and then get it better, but I think it's slowly possible to get there. And so one thing we played with, just want to show this for primordial non-Gaussianity. You can sort of improve tremendously with this field level inferences. It was just a small test we did over a power spectrum plus pi spectrum. The reason is because you get this nonlinear modeling more accurate than the regression than in the P plus B. So there's an expected improvement, and you see in some parameters, actually you have much improved. It's not like a super game changer, but for non-Gaussianity it's very interesting because typically you have to have larger surveys to get better constraints. And so here, for a fixed one, you can get more out at the same scales. I think that would be really nice. Good. So that brings me just to the conclusions. So I hope I took you to 55 years or so, going from n equals 90 to 10 to the 13. That was possible because of algorithmic improvements. I hope you got a little bit of an idea of sort of different flavors that went into this that allowed to also even grow a bit faster than Moore's law. There's really been a very different two epochs, I would say, an exploration phase where really it was about understanding how nonlinear structure formation happens, to now that we're using these as precision models and people are really obsessed of getting 1% accurate.
When did you enter the field, Oliver?
1965. When I got my PhD,
Yes.
2009.
Okay, so 2010, maybe.
Yeah, so exactly. My PhD was a lot about measuring like correlations between halo properties because people hadn't fully understand if halos are more spherical, if they are in dense environments, then they're not, and so on. So a lot of papers were in this direction. I think people are doing this now, similar things with hydro simulations where they look at things with galaxy properties. This is much more complicated because then you have also uncertainties with respect to your galaxy formation model and so on. So yeah, with the field of N-body simulations has been, I think, since 2010 about precision, and I think also I liked it a lot because it became much more rigorous. I think as a field that we sort of tried to improve the algorithms, we tried to improve the applied math side of things. Exactly. Yeah, so the largest ones now model basically significant fractions of survey volumes of state-of-the-art surveys run on the biggest machines. That's one frontier. Recent improvements, I think, that are worthy and that I've been mostly interested in is more precise at fixed cost. So you want to not use more resources than you need to. It's always, of course, cheaper just to run one bigger machine rather than to put in a year of work, but in the end, exactly. And develop faster simulations. And so these developments, I think now really, it's very interesting. So we have a very good understanding for how these are sort of mathematically work. And it allows now, you have the pioneers here in the Institute to allow to fit N-body simulations to actual data. The big open problems, dark matter galaxy connection, and I'm not sure we solved this in time for the current surveys. So it's something that will have to be parameterized and parameters that have to be marginalized over. And you've also seen the baryonic effects. And so I found this very interesting also because, one second, if you allow me, already over time. This one here. See, it's showing here and showing here. Yeah, so each one of these sort of models was built by people trying to fit certain properties of galaxies that they thought are deciding for how your simulation should be set up. Now people are doing it more in an agnostic way, where you try to emulate your parameter space and then fit actual observables and so on. But in any case, sort of the recent observations actually favor the strongest suppression models. And so I think it was kind of crazy yeah, sort of there's been very much a mismatch. So like the biggest like Horizon and Horizon AGN and TNG, illustrious TNG have a sort of baryon effects to only on very, very small scales. And that seems to be quite in contrast to observations. So, and that makes it also a bigger problem for dealing with this systematic. So all of these things sort of have to be modeled and accounted for. And that's the frontier for where we stand. So that was my last comment. And too many slides. No. Okay. Thank you.
Since we started a little bit late, we haven't had much time to actually ask some question to Oliver.
Thank you, Oliver. That was great. So, how do you define how good a simulation is? I think it depends where you're looking. So you said, okay, you can do N-body simulations with better and better number of particles, larger number of particles, which will remove the discrete noise. Yeah. And then you mentioned phase-space simulations and metric simulations, which I think are better for the nonlinear regime, right? The dense regions.
Well,
because they don't really show the same thing, right? Or do they?
So it depends.
It depends.
So it's a discussion you could have with Stefan. He knows almost more, or he knows more about this than I can say now here. So there is regimes where you have to use these techniques to get rid of certain effects, which is like these spurious clumps in warm dark matter simulations, or a little bit of collisional heating and so on. But I think we understand the level of these effects and how they affect things now. So even if they are there, it's sort of, you can control what you can say and what you cannot say.
And there's also a technical aspect, which is that the phase-space simulations are not going to 10 to the 12 particles yet.
They're not going to this, but it's a different regime.
It's
so
very difficult to go to 16, right?
You don't need phase-space simulation for that.
Yeah.
Exactly. So how do you, so just to come back to your questions, how do you test validity? So I think one thing is, we have done this industry, right? Where, for example, you need to build emulators, you need many simulations, or you need inference, you need many simulations. So you want to know, are they accurate? So you can run one very accurate one and then calibrate basically that you agree in whatever metric you choose to whatever accuracy you want.
How do you know it's accurate in the first place?
Yeah, that's the question I want to ask.
Yeah.
What are you comparing with?
Well, for example, a higher resolution simulation.
How do you know that's the universe?
Then you run an even higher one. So
assuming you use the same initial conditions.
Yeah, but this you can control.
So Oliver showed in his plot the simulations dark matter simulation, now we master. With a proper simulation, you can master with very accurately a given range of scales.
Exactly. And I think this is
nonlinear scales. You say that there was this mismatch of the inner slopes of halos.
no, but this we understand, right? So this is converged
I
results.
think it has to do with how they truncated the initial power spectrum.
Yeah, also this we understand now, sort of to what extent this depends on the truncation of the power spectrum. This was this one here. So you can run this with high resolution. It's going to always look like the black line. Those tests we've done.
Depends on initial conditions. Good.
Does not. I mean, depends on the resolved part of the. It's all resolved in this case, right? There are converged answers.
Just a comment on the early history, could I?
Do we have a question from maybe younger people before like the front row takes over?
Anglo-Saxons ask always the first question.
Oh, yeah, go ahead.
I like very much your going back into the depths of history on the early simulations. It's funny because there's also a very early paper on the angular correlation function that nobody ever cites, and it was about the same time. What was the time in which the first useful predictions for observations were made from an N-body simulation? There's the Davison-Peebles, which showed that you had to have dark matter, but I don't know if anything useful came out of growth in Peebles, did it? That simulation you showed.
Yeah, so this is very difficult to. You would have to talk with the people, right? But what I teased out from my very super. We should really just talk to the people of the time. But I mean, if you put together the evolution in the number of galaxies in the surveys and the evolution of the simulations, you see sort of that there is a coherent picture that goes sort of together, right? So that you have sort of start seeing this cosmic web emerging until sort of the mid-80s or so, and that was very clear in the simulations from the early 80s as well.
Maybe the example of your Russian movie is.
That's good.
Yes, thank you very much for a very interesting talk. Regarding the last point that you mentioned in your conclusions, is there any, I mean, more systematic way to interpolate between hydro simulations at smaller scales for galaxies and larger scale N-body simulations?
Yeah, so I'm not working on this myself, but there's several groups that are working on so-called parallelification models. So there, the idea is you take as input your power spectrum, for example, measured from a simulation, and then well, it's not actually of the sort of you add baryonic effects in a parametric modeled way to an existing N-body simulation, and then you measure the effect on the power spectrum. And then this can be absorbed.
This parametric, this parameterization, is it motivated by physics, or
yes,
it is just?
Yes, they're always motivated. I mean, there's also machine learning approaches to this, but then you need many simulations. So the parametric approach, in some sense, it says, let's assume we capture it, and let's see if all of these different simulations can be captured within a parameter space of, and then you can even put some priors based on these parameters, based on the theoretical uncertainties given the simulations that we have. So people are doing this. Yeah. The question is whether this how well this works. So at the power spectrum level, I think it works very well. So now people are sort of testing. This is like right now the frontier is does it work for bispectrum? Does it work at the field level? And so on. So. Because then you have to also take into account that it's not spherical necessarily, and so on.
Yeah. We have time for maybe one more question.
Someone young.
Well, yeah, but
So if you go.
well, I actually have one too, unless there's I'm youngish. You mentioned at some point that we don't have simulations that are both isotropic and that are like translation invariant and rotational invariant, and you showed these plots that was actually quite dramatic, where there was this quadruple looking structure in a cube.
Which one?
If you move forward, let's move like 1 or 2 slides or further. If you just move. Yeah, I guess the next one, yes. Well, anyway, is it at all possible to, because you can compute analytically how anisotropic everything is going to be?
So here you see. Right?
Yeah.
So this is what, if you run your simulation too long forward with periodic boundary condition, you always get sort of this axis aligned cross of death.
But because you know that it's dominated by the shape of your box, is it possible to compute some kernel function and then correct for it in your solver?
Well, it's not linear, so I'm not sure. I mean, maybe you could suppress the larger scale modes and say, well, you don't even try to model them. But I don't know. I mean, the problem is also whatever you see in the density is much worse in the velocities. So once you go then to want to have also accurate, say, for redshift space and so on, and